Usually when we look at a map, there's this deeply ingrained expectation of objective reality.
Oh, absolutely. We just assume it's the truth.
Right, like you're looking at a photograph taken straight from a satellite, you see a blue line, you immediately register a river.
Yeah.
You see a red polygon, you think, okay, that's a city boundary. It just feels entirely neutral,
Yeah.
like a direct reflection of what physically exists on the ground.
It is a very comforting illusion, honestly.
Yeah.
Because, we naturally want the physical world to be visible and just neatly categorized.
Mm-hmm.
The human brain prefers to interpret maps as literal, unbiased reflections because, well, takes the cognitive load off.
But the moment you actually step behind the curtain into the actual process of cartography, that objective lens just completely shatters.
It really does.
You realize you're looking at a landscape of incredibly specific choices. Every single line weight, every color ramp, every projection is a deliberate, highly curated decision.
Yeah.
And those decisions literally shape how human beings perceive reality.
It's the absolute definition of a constructed reality.
Yeah.
The map maker holds immense power over the narrative.
So, welcome to the deep dive. Today, we have a highly specific mission. We are looking directly at you, the listener, who is gearing up to crush Section 301 of the GISP exam.
The Geographic Information Systems Professional Certification.
Exactly. And we're focusing tightly on graphic representation techniques and implications. Our goal is to help you deeply understand the terms and, the underlying mechanics so you can walk into that exam with total confidence.
And we are synthesizing a really fantastic stack of materials to get you there. Rather than just memorizing a dry study guide, we're looking at the foundational mechanics of thematic maps.
Right.
We'll be drawing heavily from the history of cartography and unpacking this brilliantly dense academic paper by Miller and Wentz on spatial representation.
Which is fascinating, by the way.
It is, because these sources, they don't just tell us what GIS software does, they expose the hidden frameworks making those decisions.
Okay, so let's unpack this. Before a cartographer even opens their GIS software to draw a single line, they have to define the fundamental parameters of the project.
The ground rules.
Right. Cartography is this constant push and pull between art and science, and it's governed by 4 questions, which are who, what, where, and how.
Who is the audience? What is the data? Where is the bounding box? And how are we building this?
Exactly. And that how is heavily dictated by physical and resource limitations. Which naturally brings us to the most critical foundational building block, which is color space.
And if you're prepping for the GISP exam, you really cannot overlook the mechanics of color space. It's not just an aesthetic choice.
No, not at all.
It literally dictates your entire rendering pipeline. We're talking about the fundamental physics of how your map will be displayed, mainly focusing on RGB versus CMYK.
Right, because if you're designing a web map, you are working in an additive color model. You are literally mixing light.
Yes, RGB, red, green, blue.
And those values range from 0 to 255. But what I always found so fascinating is the physics of it. If you max out your red, green, and blue values, like all of them at 255, you are blasting the viewer's screen with so much light that it creates pure white.
Exactly. And if you add the alpha channel to make it RGBA, you're now introducing a mathematical value for opacity.
Okay, break that down for us.
Sure. So an alpha of 0 means the layer allows 100% of the light from the layer beneath it to pass through. It's invisible.
Right.
But an alpha of 255 blocks, all light from underneath, it's fully opaque. This is basically the bedrock of digital map compositing.
Right.
But the moment you decide your map needs to be printed on a physical plotter,
Oh, boy.
yeah, that entire additive math model just breaks down.
Because now you are dealing with CMYK, which is a subtractive model. You aren't mixing light anymore. You're mixing physical pigment.
Paint, essentially.
Yeah, ink on paper.
Yep.
And ink works by absorbing or subtracting parts of the light spectrum. It's like the difference between mixing flashlights and mixing finger paints.
That's a perfect analogy. And consider the implications of that shift. If you design a map in an RGB environment where colors are literally glowing, and then you just send that raw file to a CMYK printer without converting the color profile,
It's going to look terrible.
it looks muddy and muted. Because in a subtractive system, cyan and magenta absorb red and green light to leave blue. If you mix all the base inks together, they absorb almost the entire spectrum.
But you don't get black, right?
No, instead of a crisp black, you get this murky brownish gray.
Hence the need for the K channel. You have to add pure black ink, the key, to force a true black on paper. I mean, it's a completely different chemical and physical process.
Exactly. And the exam tests this because a GIS professional has to know their delivery medium before they start symbolizing data.
That makes sense.
And while we're on the subject of choosing colors, cartographers actually often prefer working in the HSV model.
Hue, saturation, and value.
Right. Hue being the actual wavelength of the color, saturation being the intensity, and value being the lightness or darkness.
Why is that preferred over RGD?
Because HSV aligns much closer to human cognitive perception. If you're trying to represent a continuous variable, like, say, average rainfall,
Okay.
stepping through the value dimension of a single blue hue is mathematically uniform and is visually intuitive. But stepping through raw RGB values to achieve that exact same smooth gradient is incredibly clunky.
I see. That makes the transition to our next core topic really seamless, because once you understand the mechanics of how your color is being rendered, you have to decide what kind of data you're actually mapping.
Right, the what?
And the sources separate maps into two distinct buckets. You have feature maps, sometimes called reference maps, and then you have thematic maps.
So feature maps are the literal interpretation of a landscape. They deal in tangible, visible objects.
Like roads, lakes, political boundaries.
Exactly. A standard USGS topographic map is a prime example of this. These are cartometric.
Meaning the spatial relationships are geometrically accurate?
Yes, the objects are geometrically accurate and can be used for hard navigation or precise measurements.
But thematic maps, I mean, this is the real meat of the GISP exam. This is where cartographers visualize the invisible.
That's a great way to put it.
You're mapping statistical data across a geographic space. Income levels, soil pH, crime rates. I mean, you can't fly a drone over a city and photograph its median household income.
No, you definitely can't.
You have to build a visual metaphor for it.
And because you are mapping statistics, the projection you choose becomes absolutely vital. Thematic maps almost always require an equal area projection.
Why is that?
Because if you're comparing data sets across different regions, the visual weight of those regions on the screen must accurately match their actual physical footprint on the Earth.
Whoa.
Otherwise, you're distorting the data's impact before the user even reads the legend.
Right. Let's get into the mechanics of these thematic maps, starting with the one everyone sees constantly, which is the choropleth map. This is where predefined areas like census tracts or entire countries are shaded based on a statistical value.
The choropleth is everywhere. It's ubiquitous, but it's also a massive trap.
A trap.
Yes, it is incredibly easy to lie with a choropleth map, whether intentionally or accidentally. If you take raw absolute data, say, the total number of traffic accidents, and map it directly onto a choropleth, you commit a critical error.
Because the bigger counties will just look worse.
Exactly. The physically largest counties, or the ones with the highest baseline populations, will immediately jump out in dark red simply because they have more people and more roads.
You essentially just end up making a population density map, no matter what variable you're actually supposed to be showing.
Bingo. In GIS, this is known as the Modifiable Aerial Unit Problem, or MAUP, and it leads directly to the ecological fallacy.
Remind me what that is.
That's where a viewer assumes that the statistical value of a large arbitrary area applies uniformly to every single individual point inside that area.
Oh, right.
So to fix this, you must normalize the data. You don't map total accidents, you map accidents per 1,000 residents. You convert absolute counts into rates or ratios.
But even when you normalize the data, a choropleth map still relies on arbitrary boundaries, like county lines. And county lines rarely care about actual human behavior or geography.
It's very true.
Which brings us to the dasymetric map. And I gotta say, when I first read about how dasymetric mapping works under the hood, it completely changed how I view spatial data.
Oh, it's brilliant. Dasymetric mapping is essentially a structural upgrade to the choropleth. It acknowledges that a variable like population is not spread evenly, like peanut butter, across a county.
Right.
It uses ancillary data sets to mask out areas where the phenomenon simply cannot exist.
Let's walk through the mechanics of that for the listener. Say you have a county with a population of 50,000 people. A standard choropleth just colors the entire county one solid shade.
Yes.
But if you overlay a raster layer of land cover data, the GIS software can identify that, hey, 40% of this county is a literal lake.
The dasymetric algorithm literally removes those uninhabited pixels from the calculation. It redistributes that population of 50,000 strictly into the remaining 30% of the landmass where the residential zones actually are.
Wow.
Yeah, it physically concentrates the visual weight of the data to match reality, completely removing the blinders imposed by arbitrary political borders.
That is such a powerful tool for visual honesty. Now, what happens when the data doesn't have boundaries at all? The study guide heavily features isarithmic maps, or isoplyth maps. These represent a continuous surface, right?
Right. Think of temperature, atmospheric pressure, or elevation. These phenomena don't just stop at state lines, right? They flow continuously across the Earth.
So how do you map that?
Isarithmic maps use interpolation. The software takes discrete data points, like weather stations, and calculates the mathematical gradient between them, drawing lines of equal value.
Contours.
Exactly, known as contours.
The historical context here from the sources is amazing. The Wikipedia source mentions Edmund Halley.
The comet guy.
Yes, the Halley's Comet guy.
In 1701, long before computers, he manually interpolated data points from ship logs to create an isarithmic map showing lines of equal magnetic variation across the Atlantic.
Yeah, that's incredible.
He was building a continuous surface model by hand just to keep sailors from getting lost at sea.
It really highlights how fundamental these geometric concepts are. And another historical breakthrough gives us the roots of the dot density map.
Oh, John Snow.
Yes. In 1854, Dr. John Snow was trying to figure out why cholera was devastating a specific part of London. And before the germ theory of disease was widely accepted, people thought it was just bad air.
Miasma.
Right. So Snow did something revolutionary. He took a map of the neighborhood and placed a single uniform dot at the exact address of every single cholera death.
He used a discrete visual mechanism to reveal a hidden spatial pattern.
Exactly. The dots didn't spread out randomly, they clustered densely around the Broad Street water pump. By plotting the exact absolute locations, he bypassed arbitrary boundaries entirely and visualized the invisible vector of the disease.
That's incredible. But I want to clarify something for the listener here, because the exam often tries to trip you up on the difference between a dot density map, a proportional symbol map, and a graduated symbol map.
Yes, they sound very similar.
They do, but the math behind them is completely different.
Let's break down the mechanics. So in a dot density map, the symbol is static. One dot equals one death, or one dot equals 100 acres of wheat. The density of the dots tells the story.
Right.
But in a proportional symbol map, the symbol itself scales mathematically to match the exact magnitude of the data point. If city A has twice the population of city B, the circular symbol for city A will have exactly twice the area of city B's circle.
So it's an unclassed infinite scale.
Precisely.
Whereas a graduated symbol map uses classes or bins. You decide that populations between 0 and 10,000 get a small circle, 10,000 to 50,000 get a medium circle, anything over 50,000 gets a large circle.
You are discretizing continuous data into specific categories just to make the map easier to read quickly.
And if your data set is incredibly complex, you might employ a multivariate display. That's where you alter the symbol's size, shape, and color all simultaneously to show 3 different variables at once.
Or, if the data involves movement, like the supply chain logistics, migration patterns, troop movements, you'd use a flow map.
The classic example there being Charles Joseph Menard's 1869 map of Napoleon's disastrous Russian campaign.
Oh, that is an absolute masterpiece of multivariate flow mapping.
It really is. The width of the line represents the size of the army. It physically shrinks on the page as they march deeper into Russia and lose troops.
And Menard tied the line directly to a temperature graph at the bottom, so you can see exactly when the freezing winter decimated the soldiers.
He layered location, direction, troop volume, and temperature into a single devastating narrative visual. It's brilliant. And notice how heavily a map like that relies on color ramps to convey intensity.
We definitely need to talk about those color ramps because the terminology absolutely matters for the GISP. You basically have sequential and divergent ramps.
Right, so a sequential ramp is straightforward.
Yeah, it progresses from a light color to a dark color to indicate a sequence from low values to high values. You use this when the data only goes in one direction, like mapping population density from 0 upwards.
But a divergent color ramp is crucial when the data has a meaningful central neutral baseline.
Exactly, like mapping temperature anomalies.
Mm-hmm.
The baseline is the historical average. If a region is hotter than average, it ramps up into deep red. If it's colder, it ramps down into deep blue.
And the center is usually white or a neutral gray.
It forces the viewer to immediately recognize deviations from the norm.
Okay, so I have a major pushback here regarding a specific type of thematic map mentioned in the prep materials.
Okay, let's hear it.
The cartogram. A cartogram physically distorts the geographic shape and size of a polygon based on a variable. So if you map total GDP, the United States and China inflate like massive balloons, and the entire continent of Africa shrinks down to a thin sliver.
Yeah, it looks crazy.
My question is, isn't that fundamentally lying with maps? You are destroying the spatial integrity of the geometry.
It definitely feels transgressive, I'll give you that. But it isn't a lie, because the distortion is the explicit, transparent purpose of the tool.
But how is that better than a regular map?
Well, remember our discussion on the ecological fallacy and MAUP? A choropleth map fails when you try to show absolute raw numbers. A cartogram is the deliberate mechanical solution to that failure.
How so?
By scaling the physical area of the geometry to match the absolute variable, you're creating a visceral visual metaphor.
Oh, I see. You're forcing the user's brain to confront the magnitude of the data by aggressively breaking their preconceived mental image of the world.
Precisely. You're sacrificing geometric accuracy to achieve statistical accuracy.
That tension between geometry and reality is like the perfect bridge to the Miller and Wentz paper. Because everything we've discussed so far, color spaces, normalization, symbol sizing, that all deals with the visual UI of the map. But how does the software engine actually understand the space underneath all that data?
And that's where this paper completely deconstructs the mathematical framework of spatial analysis.
Right. This is where we transition from the art of cartography into the hard computational science of geographic information systems.
Miller and Wentz point out a massive legacy flaw in how GIS software operates. Early spatial analysis was built on the Euclidean model.
The flat, featureless plane.
Yes. The underlying assumption built into the code was that geographic space is just a blank sheet of paper, and the distance between any two objects is just a straight line.
The classic as the crow flies measurement, which, is fine if you're measuring the distance between 2 points on a completely empty football field.
Right.
But how often does a GIS analyst work with a completely empty void?
Almost never. And that is the crux of the Miller and Wentz argument. They stress that analysts must actively intervene and select alternative geographic measurement frameworks, or GMFs.
Why is that so critical?
Because relying on straight-line Euclidean distance in a complex real-world environment will generate mathematically precise but logically useless results.
Let's use a concrete analogy here. If an analyst is routing an emergency response vehicle through downtown Manhattan, a straight-line Euclidean measurement from the hospital to the crash site might say, oh, it's only half a mile away.
But you can't drive a fire truck straight through a skyscraper.
Exactly. You have to travel down avenues, stop at intersections, and turn down cross streets.
Which requires the software to abandon the Euclidean plane entirely and adopt the Manhattan metric.
The L1 norm.
Yes, also known mathematically as the L1 norm. The software algorithm calculates distance constrained to a grid-like network. The fundamental math of spatial interaction changes entirely when movement is forced into a zigzag pattern.
And if you scale up to a global analysis, say tracking shipping routes across the Pacific, the flat plane breaks down completely. You have to force the software into a spherical geographic measurement framework.
Because on a sphere, the shortest distance between 2 points is a great circle arc. The software literally has to abandon standard geometry and calculate distance using spherical trigonometry in cosines.
But the mechanism that absolutely blew my mind was the concept of least cost paths. Because the software doesn't just measure physical distance, it can actually measure the friction of space itself.
This is incredibly powerful. A least cost path algorithm treats geographic space not as an empty void, but as a textured, resistant surface known as a cost density field.
Think of it like this, listener. Imagine you have to walk 1 mile down a perfectly paved sidewalk that has a very low cost.
Very easy.
Now imagine walking that exact same 1 mile distance, but you're wading through a swamp in waist-deep mud. The physical distance is identical, but the exertion, the time, and the energy required, the cost, is exponentially higher.
And the GIS software evaluates that friction using discrete computational approximations. It divides the landscape into a cost lattice, or cost polygons, where every single pixel is assigned a friction value based on terrain slope, dense vegetation, or even heavy traffic.
Wow, so it maps the difficulty.
Yes. The algorithm then tests thousands of routes, avoiding the high-friction pixels, to calculate the most efficient path. The shortest physical distance is very rarely the path of least resistance.
That completely redefines what distance actually means in spatial analysis, which brings us to another massive pitfall Miller and Wentz warn about.
The relationship measurements.
Right. When you ask GIS software to calculate the relationship between two-dimensional shapes, like two massive polygons representing different property parcels, how does it actually do the math? A lot of legacy software defaults to measuring centroid to centroid distance.
It finds the exact mathematical center point of polygon A, finds the center point of polygon B, and measures the straight line between them. It is computationally very cheap and fast.
But logically, it can be completely absurd. Measuring the distance between two massive, complex shapes by only looking at their center points is like saying the distance between the United States and Canada is the distance between the exact geographic center of the U.S. in Kansas and the exact center of Canada somewhere way up in Nunavut.
Right, which is thousands of miles.
It spits out a distance of thousands of miles, completely ignoring the fact that these two massive polygons share a physical border where the distance between them is literally zero.
It is a phenomenal example of how an unexamined default setting can just destroy the integrity of your analysis. Spatial analysts cannot just click the measure tool and trust the output blindly.
They have to understand the underlying mechanism.
With large, complex, or adjacent polygons, calculating average distance, minimum distance, or utilizing pure topological models is absolutely mandatory.
Let's dig into that term really quick, topological models. How does the software mathematically understand that the U.S. and Canada are touching? The study guide highlights something called the 9-intersection model.
This is the definitive mathematical framework for spatial relationships. The 9-intersection model doesn't care about distance at all. It only cares about connectivity.
Okay.
It analyzes two objects by breaking them down into three distinct geometric parts: the interior, the boundary, and the exterior.
So it builds a 3x3 matrix. It tests if the interior of object A intersects the interior of object B, if the boundary of A intersects the interior of B, and so on, testing all 9 possible combinations.
Let's apply an analogy to make those mechanics concrete. Imagine object A is a linear subway tunnel, and object B is a polygon representing a specific neighborhood.
Okay, I'm with you.
The GIS software runs the matrix. If the subway line's interior intersects the neighborhood's interior, but the subway line's boundary, its endpoint, does not, the software mathematically knows the subway passes completely through the neighborhood.
Oh. But if the line's endpoint, its boundary, intersects the neighborhood's interior, the software knows the subway line terminates inside that neighborhood.
Exactly. By analyzing those 9 intersections, the software can definitively categorize the topological relationship as crosses, contains, touches, or overlaps.
That's brilliant.
It gives the database a rigid mathematical understanding of how real-world geometries interact, independent of their size or coordinate location.
This has been a massive journey through the mechanics of mapmaking. So, what does this all mean for you, the listener, sparing down the GISP exam?
It ties back to the core concept.
Exactly. The study guide literally includes a sample question asking which statement about graphic representation techniques in GIS is true. The correct answer is, graphic representation techniques can significantly influence how geographic data is perceived and interpreted.
Every mechanism we've unpacked today proves that point. The map is not the territory. It is a highly engineered translation of the territory.
Every single decision alters the reality you present to your audience. Choosing RGB over CMYK dictates your medium. Choosing a dasymetric map over a choropleth actively dismantles the ecological fallacy.
And overriding the Euclidean default to run a least cost analysis across a friction surface entirely changes the outcome of your spatial model.
I want to leave you with a final thought to ponder, building directly on the implications of Miller and Wentz. We live in a world defined by highly complex, nonlinear processes.
The spread of an airborne virus, the cascading impacts of climate change, the fragility of global supply chains.
Right. These phenomena are intensely sensitive to the friction of their geographic environments. They don't operate on flat, empty plains.
They do not. Yet, our most ubiquitous GIS software architectures still carry heavy legacy biases toward rigid Euclidean representations of space.
So if the tools we rely on to analyze the world inherently want to flatten it, simplify it, and measure it in straight lines.
How much of our understanding of the world's most critical problems is being subtly limited by the default settings of the software we use to study them?
Are our tools blinding us to the actual shape of the problem? It is a staggering thought. The map shakes reality, but only if you understand the mechanics beneath the surface. Good luck on Section 301, everyone. Dived up, question the defaults, and remember that every line you draw is a choice. We'll see you next time.